It's the 8th end at city finals, and you're taking the last shot. If you can make this open draw, the gold medal and the spot at provincials next month is yours. Your setup is immaculate. Your line is perfect. When you push out, release. Oh no! You've turned it the wrong way. Or did you? Which way is the rock going to curl? The curl of the curling rock has stumped physicists and scientists for decades, but before we can get into how rocks move down the ice, let's first take a look at the gameplay. Curling is played with 2 sets of 44-pound granite rocks that are pushed down a sheet of ice. The goal is to try and be as close as possible to the target or the house, and points are awarded to the team whose rock is closest to the button. The number of points is determined by the opponent's closest rock to the button. So in every shot, rocks are able to curl in certain directions, depending on which way they're spun. But there's a magic to it. They don't go the way that you'd expect them to. Curling rocks have a running band, which is a circular ring on its bottom that makes contact with the ice. Let's model that on this table. Pretend my tabletop is the curling ice, and our cup is the curling rock, since its interface with our table is also ring-shaped. As you can see, the cup will turn in the opposite direction of rotation. So here's what's happening. The leading edge of the cup is experiencing more friction than the trailing edge, and as the cup spins clockwise, the friction on the leading edge is acting opposite to the motion, and the friction on the trailing edge is acting opposite to the motion on that side. But since they're unequal in magnitude, this asymmetric friction will cause a curl in the cup's path. So we'd assume it's the same on ice, right? Wrong. Ask any curler and they'll tell you that the stones will curl in the same direction of rotation. Curling ice, unlike skating or hockey ice, isn't flat and smooth. Using a technique called pebbling, ice makers sprinkle water droplets onto a prepped surface, and these droplets, once frozen, decrease friction by reducing the contact area between the rock's running band and the ice. One theory that explains the path of the rock is that the running band of the rock will catch onto each ice pebble and pivot around each pebble in the direction of motion. And though each stick and pivot motion is small, the accumulation of several hundreds and thousands over the rock's path is what creates the curl. Another theory says that as the rock slows, the front of the rock will press downwards due to the tendency of it to tip forwards. We can see this if we use a tall cup or push it really fast. This force at the front then creates more pressure, melting a thin layer of ice, and this way the front of the rock actually experiences less friction, not more. There's another one. Some propose that when the leading edge of the running band goes over the pebbled ice, it will create scratches along the pebbles like tiny valleys. When the trailing edge runs over this, it'll naturally follow the direction of the scores as it creates a force on the back of the stone. And this, of course, results in the stone moving in the direction of rotation. We don't know which of these theories hold true yet, but I hope this inspires you to try it out yourself at your local curling rink. And when you make that next clutch shot at city finals, I hope you'll think of Take Out Tina.